So, circuitry. There's 4 equations, but really only 2. What do I mean by that? Well, the 4 equations that we've used, we started out defining current. We said that current was how much charge going past in a certain amount of time. And that's why, when we went with our ski hill analogy, current became the number and speed of the skiers. There is going to be one question on your test where I don't give you the current and you need the current, but if you look closely, oh, he told me how long the circuit was on and how many coulombs of charge went through. Yeah, he told me the current, because if I give you Q and I give you T, you can find I. Or if I give you I and I give you T, you can find Q, or whatever, okay? I really don't do a big song and dance about that one. What we really focused on were the big 2. Ohm's law and Joule's law. Although Joule's law, there was several variations. I'm partial to this one. That one's not on your formula sheet, but all you do is you plug that into the V and you get IRI, which is I squared R. Why am I partial to that one? I just find when I'm solving circuits, most of the time when I'm looking at the individual circuit, I know the current and I almost always know the resistance. So if they ask me something about power, that's my fallback. VI still works. There's a third one, V squared over R. That's if you get the I by itself, V over R, and plug that in. Fair enough. Then there was a 4th equation. This was the terminal voltage equation. It said this, V terminal, I think I can make this a subscript somehow, Mr. Dueck? Yeah, I can. Equals, can I bring a symbol in here? Symbol. More symbols. Show me the EMF symbol, Mr. Dueck. Let me know if you see that curly, funky E. Getting closer. I'm in the Greek alphabet now. Getting closer. That's kind of it, but not quite. Show me a Greek letter epsilon. You saw it there, but it was backwards? We'll kind of go with that. Yeah, close enough. E and then plus or minus I little r. That's the EMF, where E is the EMF. Which is the maximum theoretical voltage. It's a constant. What changes is the terminal voltage. Having said that, even though I gave you the equation, Jordan, we kind of used Kirchhoff's laws to derive that part. We said, you know, it was just easier just to say, oh, it was the bump at the end of the chairlift. That was that little I times R, and we'll treat it that way. Okay? Then we had our ski hill analogy. We had Kirchhoff's laws. Current in equals current out. And how do we say it for voltage? Voltage gains equals voltage losses. If you ended up back where you started from, your net voltage change was 0 because whatever height you gained, you had to lose. And we treated voltage like height. Oh, and we treated like number of skiers. Okay. Then the last thing we did was rules for parallel, well, for resistors. series, add them up, parallel, we had that 1 over R equals 1 over the first plus 1 over the second. Second plus, don't forget to take the reciprocal when you're done. Okay, and then the very last thing that we did was terminal resistance terminal voltage. Rather than use that equation up there, V terminal equals EMF plus or minus I times R, I just said treat the internal resistance like a little bump getting off of the chairlift or battery. I'm going to spend some time talking about terminal voltage because that's what I did at the very, very end, and that seems to be where people misunderstand the most. Okay? So I'm going to draw a simple circuit. Supposing I said this, 30-volt battery, and I put one 15-ohm resistor here. Okay? Have I given you the EMF or have I given you the terminal voltage? Because I haven't bothered giving you the internal resistance, I haven't given you the EMF, I've given you the terminal voltage. In this case, right? Right? And I'm making up nice numbers. What would the total current flowing through this resistor be? 2 amps. Now, suppose I zoomed in on the battery. Suppose I said, okay, let's start out with this same idea where this time I'm going to give you the internal resistance. So we still have 15 ohms. And let's suppose this is 3 ohms. And I tell you that the voltage is still 30. The terminal voltage is still 30. And I tell you that we have 2 amps going through this circuit. Is that okay so far? How many volts do we lose in this bottom resistor? Low. 30, I times R, yes? How many volts do I lose going through the chairlift? Through the internal resistor? What is the internal current? What's the total current going through here? 2 amps. So how many volts must I lose going through that little bump there? 6 volts. So what must the actual EMF, which I've called the chairlift height, what must it actually be? 36. To me, in some ways, that's a better way to understand this than to fall back on the formula here. I mean, the formula works, fair enough, and it also works if we're recharging, fair enough. But I really just think about it like that. I think of it as an extension of my ski hill analogy and Kirchhoff's laws. This would have to have an EMF of 36 volts if you knew you were getting 30 volts and 2 amps in that bottom resistor. Has to. So let me see if I can find some nice pictures here. What is the terminal voltage in the circuit below? I'm going to do some really quick sketches. I'm using my tutorial from last year, but I'm trying to change the numbers. I'm hoping desperately I don't make up numbers that are impossible. If I do, I apologize in advance. So let's go with the battery like that. Yoink, yoink. Let's add a little parallel component. And let's add an internal resistor as well. So to show that that's an internal resistor, like that. And then let's suppose that I said 12 ohms, 12 ohms. Let's suppose I said the EMF is 6.0 volts. And let's make my internal resistor here pretty small. How about 0.2 ohms? Okay. How can I find the terminal voltage? Well, I would first of all look to attack. I would say, have they told me a current anywhere? Have they told me a current anywhere? No. So I'm going to write this as total resistance. Now, these two are in parallel. So the first thing that I would do is I would say, okay, 1 over R parallel equals 1 over 12 plus 1 over 12. That's 2 over 12. Reciprocal 12 over 2. I think R parallel is 6, but you guys know how to do this quickly on your calculators, yes? So I think R parallel is 6, which means I can rewrite this circuit, excuse me, as six volts, 6 ohms, and an internal resistor, what did I say, of 0.2 ohms. So now I can say, I know our total. 6.2, I'm making up numbers, this is not going to work out nice, but such is life. 6.2 ohms, I can tell you, I total. It's going to be total voltage divided by 6.2. This is not going to work out nice at all, but such is life. 6 divided by 6.2, and I get a current of 0.968 amps. So, how many amps are leaving the chairlift right there? 0.968. How many amps are going through this mathematically equivalent 6 ohm resistor? 0.968. Now, I happen to know it's going to split up 50-50 because it's 12 and 12, and I could do that if I wanted to. But the question wanted me to find what? Ryan, what did this question say? Find the... I'm telling you, the terminal voltage, this minus that, has to be that voltage there, doesn't it? Because that's the only other ski hill. In other words, chairlift minus bump has to add to a complete ski run. And since there's only one hill, that's the only complete ski run. So I could stop here and I could just say, oh, you know what? This is another way to find terminal voltage. Not on my formula sheet, but the terminal voltage is going to be 0.968 times the mathematical equivalent of that hill, 6. You're getting a terminal voltage of 5.81. You're losing about 0.19 volts going through this battery. What if I change the resistance? I could recrunch the numbers. Okay, that's terminal voltage. What if they had given me the terminal voltage and said, find the EMF? What they've really given me then is this minus that. Let's try one. Uh, 12 ohms. Oops. Internal resistance there. There's my little battery. What if they said that V terminal was, I don't know. Oh, heck, let's pick something really, 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 really nice. Let's go 36 volts. Now I would, oh, and this is, let's say, 3 ohms right there. if I want to find total current, what they've really done is they've told me that this must have been 36 volts. How do I know, Doug? Because that's the only major hill. Which means I would not go like this. I would not say, oh, total resistance is 15, total voltage is 36. That would be wrong, because if I'm using this resistor, this should be the EMF, not the terminal voltage. But what I can do is I can say, hey, I don't need to go that. I can tell you the current going through here right now. How many amps are going through that resistor? And that happens to be the total current because there's no other junctions anywhere. So I can say, you know what? Total current is 3 amps, which means total current is 3 amps, which means what did I lose going through? How many volts did I lose going through this particular battery? 9 volts, which means, oh, the EMF better be 45. Has to be. Otherwise, this circuit won't work. So there's my little rant on EMF and terminal voltage. I really, you guys have noticed, don't fall back on the equation that I gave you that much. I'd rather just wrap my brain around it because I know how to ski. I know how to solve, I know how to analyze a circuit using Kirchhoff's laws. So, are there any questions you would like me to go over? Let's see, I've got some yucky ones here that I tried. Sure, let's try this one, Mr. Dueck. From the newer one, this is number 23 apparently. This is my old one that I used to give out, and apparently I felt this one was worth doing. Oh, yeah. Sure, here's a little twist. Find a resistor. Okay, as I've said several times, if I know 2, I know 3 or 4, I can ask you to find power or voltage or current or resistance. You don't have this one. This is from the old photocopied review that I used to give out. Unless it showed up somewhere else on your newer review, but I don't think so. So you ready, Enzo? Yep. I'm going to pick on you. No. Yeah. Okay. Sure. Make this a little smaller. Yoink. Here's why, as soon as I see this, I'm fairly relaxed. Do you notice they gave me, Jordan, current in certain places? This is going to fall apart. I don't know how yet, but anytime they give me current, I kind of go, okay, as long as I'm careful, it's not too bad. I'm going to start filling in everything that I can. Did they give me the total voltage, the chairlift? No, okay. Maybe I can find that as a part B, I don't know. Well, let's see. How many amps, Enzo? Oh, first of all, I always get in the habit, that's downhill. So that's downhill, that's downhill, that's downhill. Gotcha. How many amps in this bottom chunk right here? 168. How many amps must be up here? 168. Nope. Ah, they did give me total current, right? So if 0.6 amps went this way, how many amps went this way? 2.4 minus 0.6, which is? Must be. Ooh, I now know 2 things. What else do I know in that R3? Voltage. So can someone go I times R? 1.8 times 5. Is it 9? I think it's 9 volts. Yes? Or is that a German saying no? 9? How's that help? How many volts do I lose going through here? 9. How many volts must I lose going through here? 9. I must, right? Because we can shake hands and meet up. How many volts do I lose in this resistor here? 3.6, I think, yeah. I times R. Oh, how many volts must I lose going through here? 5.4, right? Oh, and what's the current going through R2? I'm done. Because they said find resistor R2. I would now say R2 is going to be RT, sorry, T for 2. R2 is going to be voltage 2 divided by current 2, What did we say voltage 2 was? 5.4 divided by, what's current 2? Current 2 is also the current going through 1 because there's no junctions between it. 0.6, whatever. 5.4 divided by 0.6, I think it's going to be 9. Yeah, 9 ohms. Come on. Oh, you know what? I bet you part B was find the voltage. I think I've got it. Oh, Ryan, how many volts do we lose in R4? How many amps are going through R4? Do we know?
Yeah.
What? How many? Oh, ohms? Oh, I times R. In your head, 2.4 times 10. You know what? I must lose 24 volts. Let's go for an entire ski run. Starting here. Doesn't matter which way we go, but I'd probably keep it simple and go with the fewest number of hills. Can I get to the bottom like that? How many volts must that battery have been? 24 and 9, right? Must be, subtract the 3, 33? Okay. Must be 24 plus 9. It's got to be 33 volts. And you know what? That's a terminal voltage. How do I know? Because they didn't put an internal resistor in the battery. That must be, they've done the math for me already. Also because usually it's a 36 volt battery and 33. I'm betting we lost 3 volts going through this, but I don't know. Okay. Oh, what else could I have asked for? Power in any one of these? Okay. What else could I do? I could give you a using principles of physics question. Now, what kind of using principles of physics questions can you expect? Probably something like this. If I said, suppose I pull R1 out, will R2 be brighter, dimmer, or stay the same? Resolve the circuit, find how much power is going through R2, and there's your answer, comparing it to originally. Most of the time, it's either going to be opening and closing a switch, Jordan, or pulling or adding a resistor. Those are going to be your using principles of physics. And while you can do some of them algebraically, sometimes because we've gotten good at the ski hill trick, it's just as easy as to crunch the numbers. Make up some reasonable resistances if they're wanting me to add a resistor. 2 ohms, 10 ohms, 5 ohms are nice numbers to use. Oh, calculate the power dissipated by R2. Oh, V times I, 54 times 0.6. We're good. That was the part B. Figured there was a part B somewhere. Oh, hey. Here, let's try this. What's the power dissipated in the 33 ohm resistor shown in the circuit below? Is that one in your... Do you guys have one like that one? Hopefully not. Heck, I'll make it a whole new question. I'll change the voltage. I'll go 15 volts. There, now it's a new question. This is about as tough, Jordan, as I can throw at you because I never gave you any breaks. No current anywhere. Our only strategy is going to be we have to rewrite this as its mathematical equivalent. How? Well, I'm going to rewrite this as 1, and that'll be in series with that and that. How can I rewrite this as 1? Well, first of all, those two are in series. That's the same as a single what? 43. So what you don't want to do, sometimes I'll see kids go like this. Oh, 1 over R parallel, and they'll go 1 over 100 plus 1 over 10 plus 1 over 33. No, 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 no. Those are not in parallel with each other. They're in series with each other. It's going to be 1 over 100 plus 1 over 43, and I'll be stunned if that works out nice. I mean, maybe it does, but 43 is prime. 1 over 100 plus 1 over 43. Ugh. 30 point, and I'll carry some extra sig figs because this is not my final answer. I'll go 30.07. And I'd probably give you 1 or 2 marks for that. So just show me that you found it somewhere anytime. Just be neat and organized. Don't just have your pencil throw up on the page. Okay? Oh, now I can tell you. Can I do that without redrawing it? It's going to be this plus the mathematical equivalent, right? It's going to be 10 plus 30.07 plus 10. I can do that in my head. 50.07 ohms. And the total voltage is not 12 because I changed the question. So total current is going to be V total over R total. It's going to be 15 over 50.07. 15 divided by 20 plus that answer. There's my 50.07 cleverly. Oh, probably supposed to be 0.3, but I'll go 0.2996 amps. Is that enough? Let's see. What do they want me to find? The power dissipated in the 30 ohm. I know going through here, it's, what did I say, 0.2996? I could now find power. Oh, also I could do the voltage, and that's easy to do. I times R. R is 10, so 2.996 volts. Same with up here, 0.2996 amps, 2.996 volts. Can I find anything else? Is that a legitimate ski run, always going downhill? Oh, then since there's only one unknown there, I should be able to find the voltage that goes through this 100. It's going to be 15 minus 2.996 minus 2.996. The voltage there is 9.008. Oh, and now I can find the volts. And now I can find the current. It's going to be V over R, that divided by 100. 0.09008, which means that's how many amps went that way. Now I know how many amps went this way. 0.2996 minus that number there leaves me 0.20952 amps. And this is why I said to you, although power equals V times I, and I probably could solve for V, often I find I use power equals I squared R, because usually current is what I spend most of my time finding, and I usually know the resistance. Is that okay, Hakeem, or have I made a mistake? Think I'm good? So I squared times 33, you know what? 1.45 watts of power is being used up in that 33 ohm resistor. Okay. Let's try using principles of physics question, and I think I have one here. It looks like number 25. If a current, sure, this will work. The circuit shown in the diagram below, I'm trying to practice as many questions with the terminal voltage thingy as I can, because Sean, we just didn't do that many until the very last lesson, so we're adding one internal resistor. Hopefully it's not a big stretch. Yoink. Jordan, do you know why I'm smiling? Look carefully at this diagram. What do they give you that suggests this question's going to fall apart? Look at the circuit itself. What did they give you? Oh, I'm willing to bet as long as I'm medium clever and don't panic, I should be able to handle this. Okay? This is like, wow, a league game with Garibaldi. You'll get minutes. Okay? Right? Boy, I hope Garibaldi kids don't watch my video lessons. I'll be getting hate mail. Oh, whatever. They're piggybacking on my stuff anyhow. Okay. Jordan, what do they want me to find here? Which one? Okay, little r is our symbol for that. Okay. What would I do first here, folks? Something very obvious. You might not even think about it. Or how would I solve this? Any suggestions? The first thing I would do is I would say, hey, I know 2. Now, we don't use the power equation that much, but I'm telling you, if I know 2, I know 4 things. So how can I find the voltage drop through here? Well, power equals VI, so I guess V equals what over what? Okay, so the voltage drop is going to be power over current, 0.4, right? You know what? How's that help? That's, because that's the only outside hill outside of the battery. So what's my EMF? Bree, what's my EMF of this battery? Sorry? No, but first of all, that's a 7. My bad writing. EMF, remember the symbol for EMF? 9, or are you German saying, sorry. That's the EMF. What am I actually getting, though? What's my terminal voltage? So 9 in theory, but I'm getting that. What must I be losing going through there? Ah. Oh, and what else do I know going through there? Could I find the internal resistance? You know what? Look at the amount of work that I've shown. This is why the rule I have, guys, is if you find something, write it down, and that's what I look for, but I'm not going to specifically be looking for certain steps or work. Also, there's probably 2 or 3 other ways to solve this as well, but right now I haven't really shown much work at all. Over here, I'll say, okay, R equals V over I. What's the V in that resistor? 0.25. What's the I in that resistor? 0.4. 0.625 ohms. Okay, what I liked is this one had a using principles of physics. What was the... The light bulb is now replaced by a lower resistance, brighter light bulb. The terminal voltage will be, okay, cool. Well, what affects the terminal voltage? The internal resistance doesn't change because that's a chemical component of the battery. But what else appeared over here? Total current. You know what? Really what this is saying is if you replace this with a lower resistance bulb, will current go up or go down? Well, now you realize I could actually solve for R. I know V, I know A. The resistance of that bulb is V over A, 21.9. And so I could say, hey, let's put a 10 ohm bulb there and solve this circuit. Let's see if we can reason our way there. Let's see if we can reason our way there. It says it's replaced by a lower resistance or a brighter light bulb. Brighter means what? More power. This just got bigger. If that got bigger, what would happen to current? Let's find, you know what? Let's crunch the numbers. So I just said its actual resistance was 21.9. What's a nice number that I could use that's smaller than that?
50?
Yeah, I didn't go 10. I'll really exaggerate. So here is a 10 ohm bulb. Now my EMF is 9. That doesn't change. That's printed on the side of the battery. That's a constant. Oh, not I total. Well, it's 10 plus, what did we find for the internal resistance? 0.625, right? So, I total is going to be the EMF divided by R total divided by, oh, now I can kind of see what's going on. 10 plus 0.625. As that number gets smaller, what happens to this answer here? Gets bigger. So, as right? And since the terminal is your EMF minus, that's constant. That's constant. In fact, we calculated it in part A. What's going to happen to the new terminal voltage? Bigger, smaller, stays the same? Doug, what'd you say? What do you think? Let's see. This got bigger, right? So when I multiply, will this answer be bigger or smaller than original? The loss, the bump at the end of the chairlift, is it going to be bigger or smaller than it was before? Bigger. So the subtraction is going to be actually what? Yeah, it's going to be less than before. A brighter bulb, smaller terminal voltage. Kind of counterintuitive, okay? But I think we just proved it. Looking at my notes here. What else did I go over here? I did lots of crazy examples. I think now I'm going to say, hey, are there any questions from the homework, from the review, from any of the homework that you want me to go over? Because I think I've kind of roughed over everything. Yeah. From the review? Oh, from the review? 55, a scholarship question. Cool. By the way, potential difference is another word for what? Voltage. I'll find the change in height. Woo! Okay. And you looked at my answer key? Okay. I'm going to look at my answer key too in a second. It's from 1995. Ooh, a 12 marker. Nice. Well, I think I'm going to start out trying to write this as a single solitary resistor. First of all, these two are in series. Yes? So that's the same as a 22. So then these are in parallel if that's a 22. So in the interest of time, I'm going to say 1 over R parallel equals 1 over 8 plus 1 over 10 plus 1 over 22.
1 over 12.
Looking at the wrong one. I never make mistakes. Okay. So the parallel equivalent, and I'll carry some extra sig, well, I guess 3.940, so 3.94. So this whole mess is a single 3.94, and then I just have that 10 up there. So I can say this. Whew. What can I say? R total is 13.94. And V total is 9.7. They really haven't picked nice numbers here, have they? So I can tell you I total. It's going to be 9.7 divided by 13.94. So let's take this number, let's add 10 to it. There's I total. 9.7 divided by that. It'd be wonderful if it worked out evenly, but probably not. 0.6958. Okay. That's downhill. Well, I think total current goes through here. So I can certainly say this is 0.6958. Which means I can tell you its voltage, amps. I can tell you its voltage. It's going to be I times R. Hey, I can do that in my head. 6.958. Oh, and I guess now I can find this one because, right? So that's going to be 9.7 take away 6.958, 2.742 volts. And you know what? This is also going to be 2.742 volts because you can go that way if you want. Oh, and these two will add to 2.742 volts. So if I can find the voltage in one of these, then I'll see what I get from here to here. Oh, I can also do current. Current is V over R. 2.742 divided by 8. How about I put a decimal in there? 0.343. Whoop. I want to do that. 0.343 amps. What did I say total amperage was? 0.69. In the middle one, I have V over R. 0.2285 amps. That leaves me with 0.6958 minus 0.2285 minus 0.343. I hope there's some current left over to go into that right-hand one. Whew, there is. 0.1243, 0.1243. How many? I've been doing voltage in red. Let's be consistent. Times 7, 0.871 volts, 01 volts, so 0.87 volts, and 0.1243 times 15, 1.86. All right. It wants the potential difference between point X and Y. It wants that height there. Well, plus should be it. 0.87 plus 6.958. I hope it's 7.83-ish, give or take, because I've rounded off a lot. What's the answer say? 7.9? Close enough. Yeah. Is that okay? We have one that tough on the test? I would have no problem asking you to find a power or a current in either of those for resistors. Most of that, to me, is fair game. A nasty question, but fair game on the upper end of nasty. I probably wouldn't then ask you to find a voltage difference between a couple of resistors, but still. Any others? Number 8 from the review. From the very end, back near the beginning. Okay. By the way, total power, you just add them up. Okay? So what we're going to end up doing is finding the power in each one of these and then add them up. Okay? I'm going to walk you through my answer key because I think you'll spot it once I get going. So I said power equals I squared R because they gave me power and they gave me resistance, and I really want to find current. So I said, okay, I guess current is going to be divided by R square root. So that gave me the 0.528 amps. Oh, and that gave me the voltage right there of 17.42 because V equals I times R, or also V equals power divided by current. I had a couple options. Why was that nice? 24 volts, if that's 17.42, then that had to be 6.58. Oh, and that gave me the current there. Oh, and if from here to here was 17.42, then from here to here must be 17.42. Oh, and if the total current was 0.658 and 0.528 went through there, 0.13 went through there, and then I just started finding stuff, and then I said, okay, what's total power? I went I squared R plus I squared R plus I squared R, apparently. You could have gone VI, VI, and VI. Is that all right? I don't think I'm going to be asking you to find a multiple power in a circuit question. Any others? Any more you want me to go over? Or any concepts you want me to go over? Well, let me do my, which ones do I like? Now, the short answer is I like most of these. Certainly on the multiple choice, you can expect something like number 1. Somewhere on your multiple choice is going to be a question that says, which of these meters are placed properly? Remember, to measure current, the circuit must go through the ammeter. To measure voltage, you want to be in parallel with it. You want to be measuring the height above and the height below. Okay? Totally something like number 2 is fair game a gazillion times over. Number 3, we said nuke, right? So sure, something like number 7. Oh, this is just when it wants the voltmeter connected to the battery terminals, what voltage are they really looking for? Terminal voltage. So 6 minus 0.2 times little r. Heck, I can do it in my head, 5 volts. There's one, sorry, I just remembered there's one question in here that I hate. I'll keep an eye out for it. 8 we did. 9, totally good. Oh, and then B, find the power. So power is I squared R, or power equals V times I. 10 is good. By the way, 10 I wouldn't do algebraically. I would just let each resistor be 2 ohms or 5 ohms and then do the mathematical equivalent. You could do it algebraically. Sorry, I should say I wouldn't do it algebraically. I would. I'm a nerd, but if you're looking for an easy way to do number 10, just let everything, because they're all identical. Let them all be 5 ohms. Yeah, 11's fine. 12's good. Is number 14 the one that I hate? Let me just check. Oh, and then I gotta look at the answer key. No, 14 I'm good with. There's one question somewhere where the EMF is 5.5 volts. And I think when you find the terminal voltage, which should be lower, it rounds to 5.5 volts to 2 sig figs. And I didn't like that question because to me, you're like, oh, the EMF and the terminal voltage are the same answer, even though I lost some going through. I just didn't like the numbers. So I'll keep an eye out for that one. Well, you know what? I'll go with my answer key. 15 was tough, but I said, okay, constant voltage. I said, I'll let the voltage be 120 volts. That's a nice round number to do math with. And I'll let each bulb, because it looks like they're identical, I'll let each of them be 5 ohms. And I crunched the numbers. Actually, I didn't. I did this one algebraically. So here's what I really said. When this switch is open, you have removed a resistor in parallel. And so, let's see, how did I answer this one? Voltage drop and resistance are constant. Oh, I said, you know what, here, power equals V squared over R. I said, you know what, no matter what you do over here, the same voltage is going to go through there, and it's the same resistor. That's going to stay the same brightness whether you open or close this switch regardless, because it's on a circuit all by itself. So what about over here? I really want to know what happens to the amount of current flowing through Z. Well, when I opened the switch, I said Y is going to get brighter because right now Y is splitting current between mystery bulb and itself. Opening the switch, more of the current is going to go through there. So I said Y is going to be brighter, and I think I quit there because every other answer was wrong, but dimmer. Yeah, 16's fine. $18 is good. You're going to be asked to talk about placements of ammeters and ohmmeters. 19's fine. Where's the one that I didn't like? 21 will fall apart because they gave you total current. $22, again, you could do algebraically, or you could just make up a reasonable value for the resistance. 23 is good. 24, there was a part B, but it actually got tossed. For those of you who are wondering, in this stretch of wire right here, do you see a resistance at all? What that means is when you close the switch, because this has no resistance, no current whatsoever will flow to lamp B. It's going to be shut out. We haven't covered that. That's obscure. And so there, you notice it says Part A, and you notice there is no Part B. That actually got tossed that year. This was from, I can't remember what exam this was from, but it got thrown out at the marking session that year. 25, you can cross out. Oh, here it is. 27. Bad question. Okay. And the reason I didn't like this is you get an EMF of 1.54, which to 2 sig figs rounds to 1.5, and you get a terminal voltage of 1.47, which to 2 sig figs rounds to. I didn't like my terminal voltage and my EMF being the same. I mean, I realize to 3 sig figs, I'd have no problem with that, because then you can clearly see, oh yeah, I lost some volts going through the battery. The other stuff I don't mind, just bad numbers. I did B first. Well, with you guys, apparently I did a similar question to this. Oh no, they haven't told you the... Does yours connect? Yeah, okay. I'm just getting old in this diagram here. Does mine connect? What number was that? 28? I'm worried now. Yeah, these diagrams are getting a little old. I'll have to do some fixing of some type. Voltmeters, ammeters, 29 is good. Pretty much most of the rest of these I think are totally fair game. Yep, good, 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 good. I don't think I'm going to ask you much about the graph thingies. There's a couple of graph questions, which are nice, but I don't think I'm going to hit you up for that. So that kind of brings me to the end. Any other questions you want me to go over? Doug asked a good question, and for those of you at home, will I have a rechargeable battery on this test? No, it's cool, and I'm glad I always like to show it to the kids because it does explain why. Oh, that's why batteries don't charge up so fast. It's that little bump. I'm going to be hammering you with enough other stuff. I think I'm good with that. Okay. Any other questions? Be really careful with your arithmetic, with your math. I do find some sloppy math on this one for some reason. And again, if you find something, write it down so I can give you the part marks. I mean, if you get the right answer, you're fine. But if you make a sloppy mistake, but you didn't write down everything that you found, then I can't help you. Give me a second. Any others? Okay, let me pause.